Bonjour à tous. I will talk in English. So first, thanks the organizers for allowing me to present here. I will mainly talk about something related to the optimal Skorokhod embedding problem, which is based on the joint work with Xiaolu Tan and Nizar Touzi. Okay. The Skorokhod embedding problem aims to present some probability distribution on real line as a law of a Brownian motion stopped at some stopping time. So that's to say, given some Brownian motion defined on some probability space and a centered probability measure mu, the problem consists in finding a stopping time tau such that the stopped process by tau is uniformly integrable, and the random variable b tau has the given law mu. Such stopping times is usually called an embedding or a solution to the problem. Roughly speaking, there are two formulations of the problem in the existing literature. In the first one, we seek the stopping time with respect to the Brownian filtration. I mean, the filtration F is a natural filtration generated by the Brownian motion. In the second one, we introduce some additional randomness, and we consider a larger filtration for the stopping times. This problem is initiated by Skorokhod, and the various solutions are achieved afterwards. A very heuristic idea is the following. They compare a realization of a Brownian path to another well-controlled process, usually depending on the Brownian motion, and use the latter to decide when to stop the former. So if we take this well-controlled process phi to be t, a deterministic process, we get the root solution. If we take the running maximum, we get Azimuth-York solution. And if we take the local time, we get Valois solution. So more interestingly, several solutions enjoy optimality to be defined in the following. We take the root solution, for example. So this root solution is constructed through some Bohr set, which is called a barrier. A barrier is a Bohr set in R2 such that it is closed in right. So let me see for any element of this site. So we take any element that is left, that lies right to this given element. So it belongs again to this site. So such a Bohr set is called a barrier. So root constructed this solution by constructing some well-defined barrier this way as the first hitting time. Okay. And it is shown by Rust. Root solution maximize this solve this optimization problem defined this way. So the root embedding is the maximizer for this problem among all the embeddings to the given probability mu. Okay. But however, it is natural to ask if we consider some no Markovian functional phi. I mean, it is parts dependent of this form. Could we study systematically this optimization problem? And we wonder whether the optimization problem given under the different formulations, I mean the strong formulation and the weak formulations, are equivalent in general. And moreover, we wonder whether we may construct it for a general functional phi as the optimizer. If we not, can we derive some characterization for this optimizer? Okay, the main result of this talk is twofold. First, we give some weak formulation of the optimal Skorokhod embedding problem and prove the corresponding duality. And the second, Secondly, we derive some principle which is called multiplicity principle, allowing to characterize the optimizer via its geometric support. Okay, let's go. To formulate this problem, we introduce some space continuous functions starting at 0, and we define the enlarged space omega bar by the product of omega and r plus. So given this space omega bar, we define the canonical element bt defined this way. So then we introduce some filtration. The objective of to introduce this filtration is to ensure that the random element t is a stopping time with respect to this filtration. So roughly speaking, we construct some probability space, and then we will represent the embeddings, the stopping times, using the probability measures on this space. Okay, let P bar be the space of probability measures on this product space omega bar, such that B is a Brownian motion, it's an F bar Brownian motion, and the measure, and the process stopped by T is uniformly integrable. So for any given centered probability measure mu, we consider the subset P bar of mu as the set of embeddings relative to mu. Okay. As for the optimization problem, we consider this problem for restricted class of functions which are called non-anticipative. That means this functional depends the path up to theta. So for such a non-anticipative function phi, the optimal Skorokhod embedding problem is defined as the maximum of this expectation over all probability measures P bar in the set P bar of mu. Okay, this is the primary problem. So we wonder whether the optimizer exists and how to characterize this optimizer. So to do this, we first introduce a dual formulation and then establish the required duality. So let lambda be the space of continuous functions defined on R with linear growth. And let Fb be the natural filtration of the Brownian motion B, and P0 be the Wiener measure. So the dual problem is defined as following. Let H be the collection of some suitable process such that we may define this stochastic integral. So we require some technical conditions for this H such that it is unsure to be a supermartingale. So define D by the couple lambda H such that this inequality holds P0 almost surely for all omega in the space omega. And then the dual problem is defined as the minimum of the integral of lambda with respect to mu for all lambda H belonging to this set D. Okay, so roughly speaking, for the primary problem, there are two kinds of constraints. First, the Bt is required to have the given law mu, and second, as B is a Brownian motion and it's a martingale. So we banalize respectively these two kinds of constraints by introducing a stochastic integral, super martingale, and some function depending on omega t. So assume that this functional is upper semi-continuous with respect to the first component, with respect to the second component, theta. And the result is that there exists an optimizer, P bar star, and moreover, this duality holds. Okay, what is the main utility to have this duality? With the help of this duality, we may revisit the multiplicity principle which is introduced by Begley-Bloch, Haussmann, and Cox in 2014. and we provide a new proof using this duality and the optional cross-section theorem. Moreover, as every continuous martingale is a time-changed Brownian motion, we may use this duality result to study a class of continuous time martingale optimal transport problems to derive the so-called Konowitz duality. Okay, to describe the Monceau principle, we need the definition of the so-called stop-go pair. So, what is the stop-go pair? It's a couple of elements in omega bar, such that the path determines the two paths determined at the same level. It's called omega theta is equal to omega prime theta prime, and moreover, this property is satisfied for this pair. I mean, if for any new path which is not reduced to be zero, it has some strictly positive length. So for any path in omega bar, if we paste it to f, here f represents omega prime and g represents omega. So if we paste this path along f, it is always optimal to paste it to J. So that means we should. That means according to our optimal criterion, it is always optimal to paste the any path to omega bar prime than omega bar. Okay. Then for every subset of omega bar, we define another site gamma inf, such that each element could be extended strictly in gamma. Okay, with all the notations above, we may provide the main result. It's called Monceau principle. So, if there exists some optimizer and there is no duality gap, then there exists, we may find some brush site gamma, such that the optimizer is supported on gamma, and moreover, the intersection of the site of SG is a collection of all stop-go pairs. With this product is empty. So it is easy to interpret this equality. So loosely speaking, if we may find some element in this product of these two sites, such that it belongs to the site of stop-go pairs. So imagine we may cut every path along this element, along the element belonging to gamma inf, and paste it to the gamma. So we may again optimize. Optimize to improve the value of the expectation. So this is this contradicts to the optimality. So so with the duality result we have obtained, we may prove this result in another method of completely different nature. Okay, so let's go back to the roots solution and see how to interpret its construction by this principle. So if we take gamma as the support of the optimizer p bar star, and then we define we may easily compute by the concavity of the function phi for the form of the site of stop-go pairs. It is easily to deduce that Sj is right in this way, And by the monotony principle, this intersection is empty, so we may deduce easily that the barrier must be written in this form. So this can interpret the root solution. And as far as I know, other embeddings that enjoy the optimality in the literature can be interpreted by this unifying principle. Okay, to finish, I would like to make some comments. First, because I claim that there exists another site, SG star, that depends on the optimizer, such that this inclusion holds. That's to say, we find some bigger site, SG star than SJ, such that this intersection is empty. And moreover, we may extend our analysis to the multiple marginal case. That's to say, with a slightly modified formulation, we may consider a multiple Skorokhod embedding problem for vector of marginals. Obviously, this vector is required to satisfy some condition, which is called a peacock processus pour l'ordre convexe croissant in French. So for such a given vector of marginals, we may study equally the problem in the same way and establish the similar results. And the last comment I would like to make is thank you very much.
Merci. Des questions sur cet exposé?
Yes.
So some of these stopping times can be easily calculated or approximated, like the original Skorokhod one or the Dubin's one or SMIOR. At least what I remember from the original root construction, it was based on a fixed point argument which was not really constructive. But maybe with kind of these optimality considerations, you're able to compute it. So, given a random variable x, suppose you want to compute what is the barrier with some approximation epsilon. Do you know how to do that?
Actually, that depends on the very particular structure of this function phi. If, for example, if phi is equal to x square or the square root of x, so the explicit construction of such a barrier exists. But in general, yes, it cannot be very explicitly constructed if we just consider strictly concave function phi. But afterwards, this problem is studied by the potential theory and extended to the multiple marginal case. So in the recent paper of Cox and Obloy and Tuzi, where the optimal embedding is constructed in a similar way, but using more technicals. So I just want to emphasize that using this unifying principle, we cannot compute explicitly for all the existing embeddings, but we may find how it can be constructed. For example, for the Ademayor, so we know there is some increasing function, and for the running maximum, that the tau is the optimal embedding is defined as the heating time such that Bt is equal to this one. So generally, for some very specific example, the phi can be calculated. So it can be calculated for all examples. But using this criteria, we cannot recover the explicit form of this function phi. But we know there must exist some increasing function.
Merci beaucoup.